Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic will be directional derivatives and gradient. Okay, so we have some function, f of xy, function of two variables. And we know from our work on partial derivatives that the following is true, that partial f partial x at the point x naught y naught, so partial f partial x at the point x naught y naught, this gives the rate of change of f at the point x naught y naught in the I direction. In other words, the direction of the x-axis, right? Partial f partial x. Concurrently, partial f partial y, we know that that gives the rate of change, of f at a point x naught y naught in the j direction. Okay. What we'd like to do, though, eventually, and we'll do in this section, is determine, well, what is the rate of change of f in an arbitrary direction, not parallel to an axis. Okay, so we want rate of change of f at x naught y naught in any direction. And hence we'll come up with the term directional derivative shortly. Okay, so to accomplish this, where do we start? Well, we have our function, f of xy. We have our point in the xy plane, x naught, y naught. It's point p naught, right? And we have a unit vector in the xy plane only. So the unit vector u is u1i plus u2j, right? So we have some unit vector in the xy plane, and we're asking, well, if I move along that unit vector or in the direction of that unit vector, how will f change? All right, so we want rate of change of f at p naught in the direction of u, right? So we want exactly this idea right here. Okay, let's draw a picture. So here's a subset of the xy plane. Here's a point p naught, right? Here's a unit vector u, right? And just because u is a unit doesn't mean we can't move along its direction in any direction we want. So we can move along this line. So there is u. All we care about is moving along in the direction of it, right? So in particular, the arrow here indicates, so I can let s be the arc length from the point p naught in the direction of u. So the arrow is pointing in the direction of increasing s. So remember what I'm saying here is that think back to arc length. When I parameterized a curve by arc length, well, if I start at p naught, I let that be the base point for my arc, right? And as I move in this direction, I move out some length s, I land on some different point, x comma y, or x1 comma y1, go in this direction. You're talking about negative s moving in the direction of negative s out here, but you still land at some point x2, y2. So you're just moving along in some length s along this line and landing somewhere, and we're fixing p naught to be the base point where arc length is 0, okay? All right, so if this is the case, then this line that I've drawn here So this is a line that is through the point P naught parallel to the vector u, right? So x equals x naught plus su1 and y equals y naught plus su2, right? So these equations here, those are the parametric equations for the line through P naught parallel to the vector u, right? So remember, you start here in the x direction at x naught. You travel along in the some component u1. You go some arc length. You land at some new point x. Start at the point y naught in the y direction. You travel along some component u2 in the y direction, some arc length s. Land at some new point y. Okay? And notice here, if you haven't already noticed, but I've said it a couple times, we're using the parameter s, not t. And again, the convenience here is that we could change around the parameterization of our curve for different values of t. Arc length remains constant. So think back to the example from arc length where we talked about how we could look at multiple parameterizations of the same curve. Well, if we just use s, arc length stays the same no matter which parameterization that we use. Okay? All right, so, well, if that's the case, then df ds at x naught y naught gives the rate of change, where am I here, of f at p naught in the direction of u, right? So we're traveling along this line in the direction of u, right? And we're taking the derivative of the function f with respect to the arc length that we're traveling along. How far we're traveling gives us a new rate of change for different points. Okay? All right, so what is the notation here? Notation. So we have df ds, and we have this sort of u comma p naught notation down here, indicating what direction that we care about for the rate of change and what point we're talking about, right? So this is more than just the derivative at a point. It's the derivative in a direction at a point. And we abbreviate that sort of duff p naught. So this is really d sub uf, but duff is the way to think about that. So this is the derivative in the direction of u at the point p naught. And this is what we call a directional derivative. Okay? And it is the derivative of f. So derivative of f in direction of u at p naught. Okay? And notice, too, our typical notation for partial derivatives is, I mean, this is just extending that idea. All a partial derivative is just a directional derivative in a certain direction, the I direction or the j direction, right? This is just any direction. So those partials are just, this is just an extension of that idea to any direction. Okay, so let me get rid of all this and get some room to work up here. The nice thing is when we interpret these things, as far as what they mean geometrically, we don't need to necessarily reinvent the wheel here. We talked about the interpretation for a partial derivative. Well, all this is just a generalized partial derivative, so it's the same interpretation. Okay? So interpretation of directional derivative, same as that of partial derivative. Partial derivative. All right? So the idea being we have a surface in space that should be is a surface in space. All right? And z naught equals f of x naught y naught, right? then the point P naught, X naught, Y naught, Z naught is on the surface. See if I can't make a little picture over here or something. So, all right, something like that. So there's some surface in space. All right, here's a point P naught. All right, and if we kind of drop a vertical down here, maybe there's the point X naught, Y naught in the XY plane, right? So this thing is lying above the XY plane. So maybe, I don't know, maybe there's the origin. Actually, in fact, let me draw the axes in red to really make this look possibly better than it could. So maybe we'll draw the axes like that. So there's the origin. Something like that, right? So there's a point in the XY plane, and maybe, you know, so then this is going to cut through, so it'll cut through sort of like that, maybe, right? So there's your surface, right, lying above the XY plane, right? And let's see, where am I in my discussion here? Okay, yeah. So there is a vertical plane passing through P naught, X naught, Y naught, Z naught, and P X naught, Y naught, right? So there's X naught, Y naught, there's P naught, that is parallel to U and intersects the surface in a curve C. So what I'm saying is, say you picked some direction, right? Say you want to go, I don't know, like that, right? So there's direction U, right? So you want to go like that. Well, there's a vertical plane that's going to cut through that surface, right? And it'll be parallel to the z-axis. So let's see here. Can I make this look reasonably good? Possibly. So something like that, and let's see here. Maybe you had something like that. All right, and so maybe your vertical plane, which is parallel to the z-axis, sort of, and it's parallel to you. So does that look at all like anything that we would like? Yeah. So there's a plane maybe, and it's cutting through the surface, right? And it's parallel to the z-axis on one side of it because it's vertical plane, and it's parallel to you on the other side of the plane, right? Okay. And so this is going to intersect the surface in a curve. So like, in fact, it'll intersect it just like that, right? So there's the intersection of that plane with the surface, right? So it's a straight line, or at least it appears to be linear on the surface. My drawing is not necessarily the best, but so it intersects. So there's the curve C, which the vertical plane intersects. It also, I guess it's worth noting that this plane passes through this point and that point, right? Because it's vertical, it has to go through both if it goes through one. And there's the curve C that the plane cuts the surface at, right? And so the slope of the tangent line 2C at P naught, X naught, Y naught, Z naught is the directional derivative duff P naught, right? So it looks like there my curve is a straight line, so my horizontal tangent, well, my tangent will be horizontal, so I got a horizontal tangent here. Maybe my slope is 0, but that's okay. I mean, life goes on if that's true. But the fact is that whatever the tangent line to my curve here is, its slope is the directional derivative, okay? Okay, so again, this is not in any way particularly different than what we had for partial derivatives, only this time we're going in an arbitrary direction, not the direction of y or the direction of x, okay? Okay, so calculation of this stuff. How do we get these things? Well, the chain rule is helpful to us. We didn't go over it for nothing, so let's see here. All right. Calculation. So we started off with df ds u comma p naught. Okay? And we can use chain rule on this because f is a function of x and y are both functions of the arc length, right? Because arc length changes, move along different points. So we can use chain rule, and we get partial f partial x at x naught y naught times df dx. Df dx, is that right? No, it's df ds at s naught, right? And then partial f partial y at x naught y naught times, I see what's happening. Aha, I wonder if things didn't look right. This is dx ds. Yeah, that's better. Dx ds, right, not df. And this is dy ds at s naught. That looks better. Ha, okay. So there's the chain rule, remember? So it's the partials on x naught and y naught times the derivative of x in terms of s, and derivative of y in terms of s, and at the point s naught. So this is just chain rule. And also notice, remember I said this earlier, that s naught is the arc length at p naught, which is 0 because p naught on our drawing was our base point from which we measured the arc length, right? So, which is 0, since p naught is the base point from which arc length is measured. So it has arc length 0. Okay. So really we're just evaluating these terms at 0 is all I'm saying there. Okay. All right. What else? So remember the parametrics, SU1 and y equals y naught plus SU2 as such, right? Well, if we look at, so dx ds at 0, well, dx ds is just a constant u1, right? This is actually a constant, goes away. This is just s times a constant, so it's just u1, right? 0 doesn't make a difference. I mean, there's no s over here to even put in, so the 0 doesn't matter. This is a constant. And then dy ds is equal to u2, right? Again, a constant because this goes away and the 0 doesn't matter, right? And that should make some sense to us. I mean, the rate of change along a line is always going to be essentially the slope of the line in that direction, which is u1 and u2. So where am I? Okay, yeah. So therefore, back up here again, this thing, df ds up naught, well, simplifies down to partial f partial x at x naught y naught. This is now just a u1, right, times u1 plus partial f partial y x naught y naught. And this is now a u2, okay? Look right to me, yes, okay. And so I can write this actually in a different way slightly. So let me come down here. So I could write this as a dot product of two vectors, which I'm going to do, and we'll see why in a minute. So this is really partial f partial x at x naught y naught. That's our ith component of one vector, plus partial f partial y at x naught y naught. So there's one vector, and we're dotting it just like that, right? So we're dotting it just like that. So this is just the vector u, right? That's all this is, just unit vector u. And what is this thing over here? Well, let me not erase this quite yet. Let me put definition over here. Definition. That vector there, partial f partial x plus partial f partial y, it's called the gradient of f of x, y at a point p naught, x naught, y naught, is the vector, and we use the notation del f. That's a del. So this upside down triangle is a del. Del f x naught y naught is partial f partial x at x naught y naught I plus partial f partial y at x naught y naught j. So this thing here is the gradient, okay? This vector down here, it's the gradient. And it's often read, it can be read either as grad f or del f. So I'll refer to it as grad f from this point on, probably. Okay, so after all this, let's get rid of all the intermediate work and get down to the bottom line here. What is the simple way to write this thing? Well, so duf p naught. This is a simpler notation than the other one, in my opinion. So this is the directional derivative in the direction of u at p naught. It's a dot product of grad f at x naught y naught. Actually, well, I guess grad, yeah, well, how did I want to say this? Okay, so it's grad f at x naught y naught dot u, right? And so this is directional derivative at p naught x naught y naught in the direction of u, right? So that's what this is. And notice I'm not putting a vector symbol over this. It's not really standard to do that because it has its own notation, but gradient is a vector, so it's a vector quantity. Okay? All right, so we have a formula now. Let's do an example and see how we can use this thing. All right, get rid of all this stuff. Okay, let's find the derivative of what function I want to use here. How about, oops, not f of x, f of x, y. 2y e to the x squared plus sine x at the point 0, 1 in the direction of the vector 1/2 I plus 3j. Okay? So I want to find that function's derivative at the point 0, 1 in the direction of that vector v. All right, first issue here. Remember that directional derivatives are written in terms of a gradient dot a unit vector. Well, this is not a unit vector. So v is not a unit vector. But if we just normalize by its length, we know that we can get a unit vector. In fact, we can get the direction of it. So the length of v is root 37 over 2, right? And let's see here. So 1 over root 37 I plus, what have I got here? 6 over root 37j, right? And all I'm doing is dividing each component by the length to get these components here. This u is a unit vector. And in particular, u is defined to be the direction of v. Remember that the direction of a vector is just a unit vector in the same direction as that particular vector. Okay? All right. So we have a nice unit vector now. We're halfway there. We need the gradient. All right, so we need partial f, partial x at the point 0, 1. All right, so partial f, partial x, so let's see here. The first term winds up being, so e to the x squared gives you what? E to the x squared stays the same. Take the derivative out of here. That's a 2x by chain rule on this, by one variable chain rule on that. So we get what? 2x times 2y e to the x squared. This is a 4xy e to the x squared, right? Because again, that's The derivative up here is 2x, and this is e to the x squared. That stays the same as the constant. And then sine x has derivative cosine x, right? So it looks like that. That's what I got. Good. Okay. And that's evaluated at 0, 1. Okay. Plug those numbers in. Let's see here. This goes away because of the 0 in the x. Cosine of 0 is 1. That's 1. Okay. Good. All right. Partial f, partial y of 0, 1. Well, remember that this is just 2e to the x. Acts like a constant here. This is just 2e to the x squared. That's toast because it's just 0. So evaluate that at 0, 1. You get 2 times e to the 0, which is just 2, right? Yes. Is that correct? E to the 0 is 1? Yeah. Okay, looks good. Yeah. So you get 2 there, right? Sure, that's right here. Yeah, that looks good. Okay. So there's your gradient, or your parts of your gradient. So the gradient at 0, 1 is just, this is the I component, and this is the j component. So it's just I plus 2j, right? There's your gradient, okay? And your directional derivative, duff at 0, 1, right? That is the gradient of 0, 1 dot u, right? So where's u? U's up there. So 1 dot that is 1 over root 37. And 2 dot that is plus 12 over root 37. So what do you get? 13 over root 37. Okay. So there is your directional derivative in that direction at this point. Okay. All right. So not too terrible. Okay, let's look at some properties of this thing. So how does it behave as we kind of alter some assumptions about it? In particular, what we'd like to know is, for any given surface, we want to know things like what is the direction of maximum increase and the direction of maximum decrease. In other words, if we have a surface, say, I don't know, where water is flowing over it, where is the area where the water will flow the fastest downwards, where will it flow the fastest upwards, right? Or travel the fastest upwards. So let's look at properties of DUF. Okay. So we'll start by remembering a property about dot products, which said that u dot v for any vectors was length of u, length of v, and cosine theta, right? So that's a property of any two vectors. Well, the nice thing about our duff is just grad f dot u, so it's length of grad f, length of u, cosine theta. Well, u is a unit vector, so it has length 1. So this is really just length of grad f cosine theta for theta, the angle between grad f. Oops, don't need to write out grad. For between grad f and u. Okay. So we have this simpler expression for it based upon the length of grad f and the cosine of theta, right? What does this tell us? Well, it tells us that, well, cosine, of course, is stuck between -1 and 1. Excuse me. When cosine is 1, DUF is maximized and positive, right? Because the length is always going to be positive, and when this is 1, this will be the largest it can be. Duff will be the biggest it can be. This will be 1 times this length, right? And so the implication here is that theta is 0, right? And cosine is 1, theta is 0, right? And that u is in the direction of grad f, right? So think about it like this. I mean, if two angles have an angle between them, or if two vectors have an angle between them of 0, that means that they are lying in the same direction, right? There's nothing between them. There is no angle. So that means that when this is largest and positive, we're asking what is the derivative of f in the direction of grad f, okay? And so therefore, f increases, right, is most positive and maximized, increases most rapidly in the direction of grad f, right? So imagine like a mountain, and there are two paths along the sides that are kind of twisty and turning going around a mountain. But if you want to go directly up it, maybe you just go straight up the mountain, right? That's the steepest path, right? Going right up the face. So that would be the direction of grad f for the mountain. And we'll see actually that's more true than it even sounds at first. Okay, so on the other side of this coin, cosine is -1. That's possible. That means that this is maximized, but it's negative, right? Because it's now the length. It's now the length of, or the negative of the length of grad f. So it's maximized and negative. All right. And so that implies that theta is equal to pi, right? And u is in the direction of negative grad f, right? U is in the direction of negative grad f, because when this is -1, that's going to be, so actually, though this theta here being pi implies that the angles lie on opposite sides of the circle. So like, you know, here's grad f going that way, and here's u going this way. So grad f goes like that, and u goes like that. And this is certainly the direction of negative grad f, right? Okay. So that means that f decreases most rapidly in the direction of grad f, right? You want to get down from the mountain, well, you can either take the windy path or you can just slide down the inclined face. Well, that's the direction of negative grad f. I should have written negative grad f down here. Negative grad f, right? Okay, so that's maximized increase and decrease. Well, one more thing to look at, so let's go up here. So what about when cosine is 0? All right, well, when cosine is 0, duff is 0, right? So there's no change in the function, right? And the implication here is that u and grad f are orthogonal to each other, right? E.g., theta is pi over 2, right? Because cosine is 0 at pi over 2, at 3 pi over 2, things like that. So when that's the case, u and grad f are orthogonal, right? They're at right angles to each other when the angle between them is pi over 2 or some multiple of that, some odd integer multiple of that, right? And so as a consequence, duf is equal to 0, so f has no change when u is orthogonal to grad f. And we'll see this shortly, but think to yourselves right now, I mean, think about what a level curve in the plane is. Remember, level curves are curves in the plane where the function maintains a constant value. So if that's the case, there's no change in the value of f. Well, it should be the case that along a level curve, right, that u and grad f should be constantly orthogonal to each other because there is no change in f along a level curve. And we'll see that shortly. Okay, so example of all this stuff. Let's get rid of this stuff here, and then we'll test this out in a function. I will show a more real-worldy example at the end of the lecture, but for right now, we'll just kind of play with the arbitrary function. So let's find the directions in which f of xy is x squared over 2 plus y squared over 2. Let's say it increases most rapidly. At the point 1, 1. Okay. Well, remember that the most rapid increase, so most rapid increase is in the direction of grad f. All right? Well, let's get grad f and get its direction then. Okay? So grad f 1, 1. Well, the derivatives here are pretty easy. So this is partial f, partial x here is 2x over 2, which is just x. So that's xi. And the same thing with the y. Partial f, partial y is just 2y over 2. So that's just yj. Right? So that's grad f at the point 1, 1. Oops. Point 1, 1 like that. This gives you I plus j. Well, that's not a unit vector, so it's not the direction. So the length of grad f is root 2, right? And so the direction of grad f is 1 over root 2i plus 1 over root 2j, right? So that's the direction of grad f. And this is the direction of most rapid increase. And in fact, the rapid increase there, the rate is this right here. So it's root 2, right? So this is the direction of most rapid increase. This is the rate of increase. Remember, the rate of increase when it's most rapid is just the length of grad f. Okay? All right, so how about the same question, only now we're going to look at how about rapid decrease? So decreases most rapidly. Well, the nice thing is I've already done all the work we need up here. So remember the direction here. So most rapid decrease is in the direction of negative grad f, right? Well, that would be what? Negative 1 over root 2i minus 1 over root 2j, right? That's the direction of negative grad f. And the rate there would be negative root 2. The rate there would be negative root 2, right? Because it's just the negative of the length of grad f. So that's the rate of decrease, right? The rate of decrease. Okay. All right. We can also ask, when does it have no change? So let's get rid of the increase stuff and the decrease stuff and look at when does it have no change. All right, so has no change at the point 1, 1. Well, so it has no change when u, which is u1i plus u2j, is orthogonal to grad f, right? That's when it has no change, when they're orthogonal. So grad f dot u should equal 0, right? And so since grad f is just I plus j, so I plus j dot u1i plus u2j, right? That means that this equals 0. So the implication there is that u1 plus u2 equals 0, and that u1 equals negative u2, right? So any unit vector where this is true will actually work here. So as an example, u equals I minus j would work just fine, or also negative I plus j would work as well. And so the directions of no increase, of no change, I should say, no change are the directions of those vectors. This has length root 2. So does its converse. So I should say up here, u equals negative I plus j. Both of those are the directions that we care about here. These both have length 2. I should say u1 and u2 maybe. Yeah, there you go. So there's u1 and u2. They both have length root 2. Excuse me. So length of u1 equals length of u2 equals root 2. So the directions are just 1 over root 2I minus 1 over root 2j, or negative 1 over root 2I plus 1 over root 2j, right? Both of those directions will give you no change. Okay, so not too bad. All right, so I mentioned this earlier, but let's get down to this again about the whole tangent curves to level, or tangent lines to level curves. I said that it makes sense that on a level curve, gradient and u should be orthogonal to each other, and that's going to be true. So tangent lines to level curves. Okay. So let's see here. How do I want to say this? So f of x equals c along a vector path, r of t equals x of t I plus y of tj, right? So there's your vector path. This is a level curve. So then the path is a level curve of f, right? So let's see here. What do I want to say now? So therefore we have f of x of t, y of t equals c. And you could take ddt of both sides here. Take ddt of both sides, right? And what do you get? So you take ddt down here, and you got to use chain rule on that side. And ddt of a constant is just 0, so that's easy. So over here we use chain rule, partial f, partial x, dx dt, plus partial f, partial y, dy dt, all equals 0, right? And you can move things. This is just chain rule on this component over here. And you can move this around, make it a dot product again, and you'll see that, so I guess this should be equals, equals, equals. Let's see, so this is partial f, partial x, I, plus partial f, partial y, j, dot, dx, dti, plus dy, dt, j, right? Okay. So there's the gradient again. Good. And this is actually just r prime, right? Tangent vector, right? That's all this is. There's r, and that's r prime. Okay, good. So, and this is equal to 0. Is that right? Yeah. Looks good. Okay. So, the fact is, the gradient is orthogonal to a tangent vector. Okay, terrific. Well, we kind of figured that already. So, let me erase this and make some room. Okay, now is there a way I can condense this down? So r prime of t naught is the tangent vector, to the level curve at the point x of t naught, y of t naught, right? So some point on the level curve, there it is, there's the derivative to it. And gradient, the gradient at that point. So it's a lot of points here, but don't let it confuse you. So grad f at that point is orthogonal to r prime of t at the point x of t naught, y of t naught. Well, what I'm saying here is that if the gradient is orthogonal to the tangent vector, and the tangent vector is tangent to the level curve, then the gradient should be orthogonal to the level curve at every point. Well, no surprise there. So the punchline, we already knew it from earlier, but still now it's explicitly written out. The gradient at x of t naught, y of t naught is normal to a level curve at the point x of t naught, y of t naught. So that's a lot of writing to say something pretty simple here, but the bottom line is that, let me draw a picture, maybe that'll help show what's going on. All right, so here's a picture. So there's a level curve, right? Y, x, level curve, xt plus yt, I, j. It's a level curve of some surface, okay? And then, so pick a point t, or t naught, right? So maybe, I don't know, maybe it's there, right? So the vector tangent to that looks something like that, right? So there is r prime of t naught, right? There is the tangent vector to the level curve at that point, okay? Well, the gradient is orthogonal to that. So the gradient, that's a right angle. So there's gradient x of t naught, y of t naught, right? There's the gradient. And notice that if the gradient is orthogonal to the tangent vector, the gradient is orthogonal to the surface or to the level curve at every point. Okay, so that picture basically says what this says in a much easier way. Okay, so pictures are nice. Okay, now, what we want is we want an equation for the tangent line to the level curve. So let's get rid of this. We want an equation for the tangent line to the level curve. So want equation for tangent line to level curve, right? So what do we need to do? Blah, 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 blah. Okay, so we need the tangent vector at a point p naught, right? Okay. Well, we don't have it, but we do know, we know grad f is orthogonal to tangent vector p naught, right? Okay. So let's see here. So we have a point. Can we do this out? Maybe we can do this out. Yeah, this is kind of interesting. We have that point, right? We have the normal vector, grad f, which is maybe ai plus bj at that point, right? And so we want the line through that point, that normal vector there. Well, think about it like this. So remember old point slope form. So we've got like so remember point slope looked like m x minus x. That's point slope form for a line, right? Well, it's back. So we have points. That's fine. This vector is just like a line with a slope, right? It's 2D, so just a line with a slope. In particular, its slope is change in y over change in x. So this thing's slope is b over a, right? So it's just b over a. So let's try plugging this in here. So what do we get? Sure, this is going to actually look proper, yeah. Y minus y naught equals b over a, x minus x naught. What do I want to come out with here at the end? That, okay? So we can multiply both sides by a, and that's a decent equation. Let's see here. A plus b y naught. Well, let's see. Have I screwed things up here? Possibly. Multiplied by, should it be a over b, change in y over change in x, plus, let's see here. So let's keep going with this. So a y minus y naught minus b x minus x naught equals 0. Does it look right to me? Well, something may have gone wrong here, but okay. So I have to go ahead and scrap that and add it to the notes later on, but I don't want to spend too much time on this. So actually, so your equation should actually look like that. Yeah. So this is the equation for the line through the point P naught, X naught, Y naught, normal to the vector AI plus BJ, right? And notice this is just the same thing as a formula for a plane with a normal vector, only we've cut out the k term. This is just a formula for a plane with normal vector AI plus BJ plus CK. We've cut out the k term here, okay? Okay, let's go ahead and use that formula and get a tangent line here. So let me get rid of everything over here, actually. Let's see here. Find an equation for the tangent line to the hyperbola y squared minus x squared equals 9 at 4, 5. Okay, so let's see here. All right, so we have this equation for hyperbola here. All right, well, this is a level curve, right, of the function f of xy equals y squared minus x squared, right? It's when this is equal to a constant value. So this is a level curve of that function. So the gradient of f at that point is what? So it's negative 2xi plus 2yj evaluated at 4, 5. Right? So that gives you what? Negative 8i plus 10j, right? So there's the vector normal to the hyperbola at that point, right? And so the tangent is the line, what? So it should be negative 8 times x minus, what's our point, 4, 5, x minus 4 plus 10 times y minus 5 equals 0. And let's see, fiddle around with this stuff, plus 32 plus 10y minus 50 equals 0. Let's see, keep messing around with it here. So you got negative 8x plus 10y. That's a negative 18. It's a positive 18. Scoot things over, and you get y equals 4/5 x plus, let's see, 18/10 is 9/5. Yes. Okay, so there's your line for your tangent. Let me draw a picture. Let's draw it over here. Okay, so here's the hyperbola, or at least the part we care about. Y squared minus x squared equals 9. It's down here too, but we don't care about that part. The point 4, 5 is maybe right there, right? So there's 4, 5. Right? The tangent line to it is like that, right? There's the tangent line. And the normal vector, the gradient, looks like that, right? So this is negative 8i plus 10j, normal to it. And this is the line y equals 4/5 x plus 9/5. And so there's tangent line. There's the gradient vector. Okay? Okay, so one more big topic here, then we'll do interpretation and be done with this section. So that's tangent lines. Functions of 3 variables, well, not a whole heck of a lot changes, which is good. So functions of 3 variables. Right, so here the gradient is just partial f partial xi plus partial f partial yj plus partial f partial zk, right? And duff is just partial f partial x u1 plus partial f partial y u2 plus partial f partial z u3 for a function f of x, y, z and a unit vector u1 I plus u2j plus u3k. So notice here we're now working in a 3D surface and looking for a 4D function. Okay, so and all properties are the same. Okay, so an example. Look at this very briefly. So f of x, y, z is x sine y, z. So let's find the derivative of f at the point 1, 3, 0 in the direction of I plus 2j minus k. Okay? So we need the gradient of f at the point 1, 3, 0. Okay? So what does grad f look like? Let's see here. So with respect to x here, you get sine yzi. Respect to y, you get x cosine yz and pull the z out. So you get plus xz cosine yz. And then with respect to z, again, it's x cosine yz, pull the y out. So you get xy cosine yz. I evaluated at 1, 3, 0. So you plug stuff in. Let's see here. So sine of 0 is 0. That's gone. Let's see here. This has got a z, so that zeroes out. Cosine of 0 is 1 times 3. So you get 3 at the end of all that as your gradient. And let me erase the top of this. So you have your gradient. Let's see here. So your v is not a unit vector. So your v has got length 1 and 4 is 5 and 1 is 6. So unit vector in the direction of v is 1 over root 6i plus 2 over root 6j minus 1 over root 6k. Again, because this vector has length root 6. This is a unit vector in its direction, right? And where am I here? And so duff at that point is equal to gradient dot this thing. Is that right? So yeah, so it's gradient of 1, 3, and 0. And actually what I should say down here, I'm being very sloppy here, aren't I? That should have a j, and that should have a k, and this should be 3k. Yeah, I'm being very sloppy here, but this is still a vector, still 3k. Okay? So this is duff times, this thing is u, so that's duff times u. So that's 3k dot this garbage, gone, gone. So that's minus 3 over root 6. 3 over root 6, yeah. Right? So these two together, you do get minus 3 over root 6. So this is the derivative in the direction of this vector at that point. Okay? Okay, one more thing to do here, and then we're done. So it's important to see, I mentioned earlier with the mountain example, let me draw a picture up here that kind of reiterates that. So significance of the gradient. And why is it important to us? Well, so here's a topographical map of, say, a hill. Right? And let's put elevations in here. So 100, 200, 300, 400. So these are elevations above sea level, right? And so think about it, and these are all level curves here, right? So if you walk around the hill in a circle along the level curve, or in this shape along the level curve, your elevation is not going to change. You're not going to get any higher up, right? But what is the path of steepest ascent? Well, if you start down here and you proceed directly up the side of the hill, right, that is the path of steepest ascent to the center there. So say you have something like, so let's see, so that's normal there, and then maybe that's normal there, right? And maybe that's normal there, and then let's see here. Is that all my curves? 1, 2, 3, and then maybe this goes like that, right? So there's your path of steepest ascent is against the grain of the level curve, right? Level curves take you around the same elevation. You can walk around the hill like that, and you'll be at the same elevation on the curve. Go right up the side of the hill, and you notice that, so let me say this in words. So on each level curve, elevation is the same. Elevation is the same. The path of steepest ascent is going straight uphill, perpendicular to the level curves, and that is in the direction of the gradient. Okay, so this path here, where it's all perpendicular to the level curve, that's the path of the gradient. Okay, that's it for this section.